Put your brain in the game. In physics, we talk a lot about mass. I mean, you hear it all the time. Force equals mass times acceleration. Energy equals mass times the speed of light squared. But how many of us really know what mass is? Ooh, I gotta lay off the cookies. Can you tell me what your mass is?
My mass on Earth? I don't know what my mass is, but I know what my weight is.
Do you know what your personal mass is?
It's 9.81 kilograms in relation to gravity.
Cool. When I'm standing on a scale, gravity is pulling me down, right? Well, the scale would have to exert a force back or I'd sink into the ground. The scale records how much force is needed to keep me from sinking. That's my weight. But the problem with weight is this. If I wanted to lose weight, all I have to do is come up here into the mountains. You see, I weigh less up here. And if I wanted to gain weight, all I'd have to do is come down here to sea level. You see, your weight changes depending on where you are. Here, at sea level, I'm closer to the center of the Earth, so gravity has a greater effect on me. Of course, the difference is a lot smaller than this. High in the mountains, gravity has less effect on me because I'm farther from the Earth's center. When you're up on an airplane, you're even farther from the Earth's center, so you lose weight when you fly. Excuse me, do I look thinner to you?
On the moon, gravity is much less, about 1/6 of gravity on Earth. So if I were to weigh 180 pounds on Earth, I'd only weigh 30 pounds up here.
That's why, in physics, we're more interested in an object's mass than its weight. Weight changes. It's not constant. But whether I'm here or here,
Or here, my mass is gonna be the same. My weight is different, but my mass is the same. So, what the heck is mass?
You see that? That's Jenny Curry. She's only 15 years old, but at the age of 14, she was the ladies' street champion at the 1998 X Games. So whether she's in the vert, doing the gap, or flipping through the air, she has got mass. And because she's got mass, she's got inertia. Jenny, you have got inertia.
Is that a good thing or a bad thing?
It's a neither thing. You see, just standing here, you are proving Newton's first law of motion in physics.
An object at rest tends to stay at rest.
Exactly. Unless acted on by an outside force, you're not gonna move. But if I do this,
An object in motion tends to stay in motion.
right, unless you hit another outside force, you can just keep on going forever. The idea is that an object tends to keep doing whatever it's doing. That's inertia. Just sitting here like this locomotive has a lot of inertia because it would take a lot of force to get it to really move, right? And once a locomotive is underway, it wants to keep on going. It also has a lot of inertia when it's moving. Inertia doesn't have to do with weight. It has to do with mass. Good chicken. Mass measures how hard something is to move. Mass is the measurement of inertia. The more mass something has, the harder it is to move. The larger its inertia. Can I get some help over here, please? Now, we have weighed each one of you guys in newtons. That's the metric equivalent to pounds.
700 newtons.
And you?
620 newtons.
Okay, now what's gonna happen when you guys go off the edge right here?
Gravity pulls us down.
Right, gravity accelerates you down. Now, gravity is gonna be pulling you down with a bigger force than you.
Right, because I weigh more.
Okay, so which one do you think is gonna reach the bottom first?
Well, it should be him because gravity's pulling him with a bigger force.
Okay, let's try it. Hey, what happened?
We both got to the bottom at exactly the same time.
Yeah, but gravity was pulling you down with a bigger force. Shouldn't it have pulled you down faster?
Seems that way.
Because Dave has greater weight, gravity is exerting a greater force, but he also has greater mass, which means he's harder to move. Gravity exerts less force on Kaylee, but he has less mass, so he's easier to move. It ends up equaling out, and they hit the bottom together. That That's why when you drop objects of different weight, they'll hit the ground at the same time because of mass and inertia. It also proves that gravitational and inertial masses are equivalent. The mass that's important in weight and the mass that provides inertia are equal. You can use one to determine the other.
So our mass is 450 newtons?
Well, not really. A newton really isn't a measure of mass, it's a measure of force, like pounds. How much force gravity is pulling you down with. In the metric system, a unit of force, like a pound, is called a newton, in honor of Sir Isaac Newton, who I'm supposed to look like here. Now let's say we had a box of newtons, the cookies, with a mass of 1 kilo. It would take exactly 1 newton of force to accelerate a 1 kilo box of newtons 1 meter per second squared. So a kilo is all about mass and acceleration, get it? It's inertia and weight and mass all rolled up into one, like a great physics cookie. Okay, Jenny, so what's your mass?
50 kilos?
And how much force is it going to take me to accelerate you 2 meters per second squared?
100 newtons.
Okay. Kilos aren't about how much you weigh. They're about how much force it takes to move you. Here's the great thing about mass. It's the same whether I'm here, here, here,
Or here. Mass stays the same. Look at weight. It's different all over the place. Worthless. But mass is constant. Take this baseball. It has the same mass. It takes just as much force to throw.
This is Mission Control to Shuttle. Is someone playing baseball up there?
as it does on Earth. Jenny, are you ready for some rotational inertia?
Yeah.
So far, the kind of inertia we've been talking about has been in a straight line, a kind of linear inertia. But these guys don't just go in a straight line, they spin. When something is spinning, it still has inertia. It'll keep spinning until something stops it. We call that kind of spinning inertia rotational inertia. Get it? Spinning, rotation. Oh, I think I'm gonna be sick. When an object's not spinning, it tends to resist being spun. Just like an object at rest tends to resist moving. It has inertia, and we have to apply a force to overcome that inertia. And that force has to be off-center. If I push you at the center...
I move, but I don't spin.
Exactly. But if I push you off-center...
I spin.
Right. Now, that off-center force has a special name. It's called torque. And torque is what we use to spin something. Good job, Alice. To get going, overcome linear inertia, a skater applies a force by pushing off on their skate. But how do they apply a torque to spin? Let's go to the sports figures blackboard and take a look.
You know, inline skaters spend about as much time spinning as they do going in a straight line. But to do a trick with a spin, they have to apply torque. Where do they get the torque from? There's only two ways to get the torque that's needed to spin. See, now she's pushing off with that outside foot, giving a torque in this direction, which makes her spin in this direction. Another way to get the torque is to throw some of your body's mass at the problem. Typically, somersaults are done by throwing the mass of the head and shoulders in the direction you want to spin. No torque, no spin. It's as simple as that. I'm Sal Masakela from the Sports Figures Blackboard.
The torque needed to spin something is a function of mass and the shape of that mass. Now, some shapes are more difficult to spin than others. Now, this bowling ball has a mass of 5 kilos, and this barbell has a mass of 5 kilos. Okay, Jasante, let's spin them. Nice.
The bowling ball spins easily. The barbell's really hard to spin.
Right. The mass is the same, but the torque needed to spin them is different because of their shape. So for gravitational inertia, we can't use mass as a measurement.
Because it's the shape of the mass that counts.
Right. Just like mass measures the resistance to acceleration, for an object's resistance to being spun, we use moment of inertia. Ready? Let's pause for a moment of inertia. To get something to move, we apply a force. In an equation, that looks like this. Force equals mass times acceleration. To get something to spin, we apply a torque. In an equation, that looks like this. Torque equals moment of inertia times alpha, or angular acceleration. Mass is replaced by I, moment of inertia, how much an object resists being spun. And now, back to the show. That's why skaters will tuck to do somersaults. Bringing their mass in reduces the amount of torque they need to spin. The torque needed is way higher to spin in a layout because you have a greater moment of inertia. It's harder to get yourself spinning.
Okay, so what did we learn?
When an object at rest stays at rest, and an object in motion stays in motion.
That's called inertia.
Inertia is a function of mass, so mass isn't weight, but how much inertia an object has. How hard it is to move or stop.
Kilograms are a measure of mass, and for spinning, the measure is moment of inertia.
And to get something to spin, you must apply an off-center force called torque.
Whoa, all right, that's great.
Well, that's it. We'd like to thank everyone for helping us out today. Jenny Curry, and of course our students, Meredith and Jasante, Mac, Edgar, Ellis, and the X-Trials for helping us out with ESPN Sports Figures Inline Inertia.
Man, I gotta lose some mass.
I'm Chris McHenry, back in the ESPN studios. We'd like to thank all of today's athletes for donating their time, and thanks for watching. We'll see you next time on ESPN Sports Figures.
ESPN Sports Figures is presented commercial-free for educators to tape and use in the classroom. For a free teacher's curriculum, to order the Sports Figures series, or if you have questions or comments, visit our website, sportsfigures.espn.com. You can also call 860-766-2000. This has been a presentation of ESPN, the worldwide leader in sports. For more, log on to espn.com. Sports Figures, put your brain in the game.